So here we're going to look at a famous recursive pattern, which I'm calling the Leo function. So first let's identify some features of it. The first is that this one actually has two base cases. When n equals 0, that returns a set value, and when n equals 1. There is a recursive case too. This is essentially when n is not 0 and n is not 1. So if n is any other value besides 0 and 1, then it's going to be doing the recursive stuff. So that's recursive. Those two are going to be the base cases. So let's actually look at those base cases. If we do Leo of 1, that's definitely going to give us 1. Leo of 0 will definitely give us 0. And Leo of -1 is going to cause a lot of trouble because this is going to be putting in a negative input, and then this makes that input smaller, which means we're not getting closer to the base case. So this is a stack overflow exception, this is crashing, it's bad. So we're going to get into more detail about this Leo function now. So let's look at what happens if we try to do Leo of 2. What the algorithm says is that we should do the Leo function again with the input being 1 less, plus the Leo function again with the input being 2 less. So fortunately we know what Leo of 1 is. We already said that that's 1, and we know that Leo of 0 is 0. So we're going to do 1 plus 0, which is the value 1. So that's what Leo of 2 equals, just the number 1. Let's look at Leo of 4. This is where things start to get a little bit more complicated. If we wanted to do Leo of 4, that means, based on this recursive definition, we would have to do Leo of 3 plus Leo of 2. And if we wanted to do Leo of 3, though, we would have to do Leo of 2 plus Leo of 1. Now I know we technically know what Leo of 2 is, Leo of 2 is, and Leo of 1 is, but I want to show you what actually happens on the computer. The computer goes, all right, what's Leo of 2? Well, that's, I shouldn't need 2 arrows. It's going to be Leo of 1 plus Leo of 0. Then this Leo of 2 will also be Leo of 1 plus Leo of 0. So you get this kind of messy tree. We know that Leo of 1 is 1, Leo of 0 is 0. So we add these up and we get that, and oh, let me do these two. Leo of 1 is 1, Leo of 1 is 1, Leo of 0 is 0. And we start adding these values up the tree, so 1 plus 0, that's 1. So remember, we knew that Leo of 2 was going to be 1. And then 1 plus 0, once again, that's 1. We bring that up. 1 plus 1 is 2, so we've got 2 plus 1 gives us the value of 3. So it turns out that Leo of 4 is the value 3. It's really just the sum of all these 1s that we got at the bottom. Some of you might know what this thing is at this point. This is actually something called the Fibonacci sequence. And the reason why this is called the Fibonacci sequence, let me go up here a little bit, is the Fibonacci sequence looks something like this. 2, 3, 5, 8, 13, 21. And essentially the way that you get the this term in the sequence, the 8, is you add up the two previous terms, the 3 and the 5. And that's essentially what this says. To get the nth term in the sequence, you get the previous term plus the term before that. So to get the 8, you do 3 plus 5, and that gives you the 8. So this is a fairly short, in my opinion, way to write a function that gives you a pattern that's pretty complex. The dilemma for using the Leo function, or the recursive definition of the factorial function, or Fibonacci sequence function, is that it becomes very inefficient for large values of n, and by large values I mean like 46. If you wanted to calculate the 46 Fibonacci value using the Leo function, it would take you about 4 billion function calls. It would give you a value that almost overflows the integer range. So it's going to be really, really big. So there are ways to do this that are much faster than doing a recursive solution. We can actually do the Leo function in an iterative manner. So here is what someone could write the Leo function using a loop instead, and I'll show you how it would work. So let's say we want to do Leo of n. So it doesn't hit our two initial cases. They're not base cases because it's not a recursive function. But the way it would work is we would set a previous to be 0 and a current to be 1. And because our n is bigger than or equal to 2, we calculate the temp to be the previous plus the current. So 0 plus 1 is 1. We make the previous take on the value of the current. That's weird. The previous will get the value that current currently has. Oh, I said it twice again. And current will get the value that temp has. And n will go down by 1, and we check again. Is 4 bigger than or equal to 2? Yeah. So we repeat the process. Our temp is the previous plus the current, and the previous plus the current, 1 plus 1 is 2. We make the previous take on the value of current, and we make current take on the value of temp. And then we make n go down by 1 to 3. Is 3 bigger than or equal to 2? Sure. So we go again. The temp is the previous plus the current. 1 plus 2 is 3. We make the previous take the value that current currently has. We make current take on the value of temp. And then we make n go down by 1. And 2 is bigger than or equal to 2, so we're going to go one more time. We make the temp be the previous plus the current, which is the value 5. And then we make the previous take the value of the current take the value of the temp, and n goes down by 1. And because the loop is done, because 1 is not bigger than or equal to 2, we return the current value, which was the value 5. And so what this is saying is that Leo of 5 is the value of 5. And to show you that in the sequence, we had 0, 1, 1, 2, 3, 5, 8. If this is 0 position 1, 2, 3, 4, at position 5, we do get that 5 is the Fibonacci number. So recursion can be nice for writing very simple solutions, but sometimes it's not the most efficient way to do it.